Some questions don't need answers right away, only time, stillness, and curiosity. Like, what can a machine truly understand, or can a problem be too complex for even the most powerful computer? Welcome to Byte and Night. Let the gentle sounds soothe your mind as we drift into the beautiful logic of computer science. Tonight, we begin with one of the simplest models of computation, finite automata. Imagine a system so minimal, so mechanical that it can only exist in one state at a time. Yet somehow, from these tiny steps, we can recognize patterns, understand language, and glimpse the soul of algorithms. Let's begin. Imagine you're building a vending machine. It accepts coins, follows a sequence, and gives you a snack, but only if you insert the coins in the right order. Behind the scenes, there's a simple system keeping track of what you've done so far. That system is a kind of finite automaton. A finite automaton is one of the most basic models of computation. It's like a very simple computer that can only be in one state at a time. It reads input, like a string of characters, and based on what it reads and what state it's in, it moves to another state. That's all it does. But that simplicity is also its beauty. Let's walk through an example. Suppose you want to design a system that accepts any word made up of the letters A and B, but only if it ends with AB. You could create a finite automaton that starts in a beginning state, transitions based on each character, and ends in an accept state only if the last two letters match A, followed by B. It doesn't need to remember the whole word, just enough to know what state it's in now. This is the power of finite automata. They don't have memory the way we usually think about it. No stack, no variables, no history. But they do keep track of context through their current state. That's enough to recognize patterns in text, validate user inputs, or even check if a string follows a certain format. There are two main types of finite automata: deterministic and non-deterministic. In a deterministic finite automaton, or DFA, every input leads to exactly one possible next state. Think of it like a choose-your-own-adventure book where each decision has only one path. If you read an A from a certain state, there's one and only one place to go. In a non-deterministic finite automaton, or NFA, you can have multiple choices for the same input, or even transitions that happen without any input at all, called epsilon transitions. It's like having several versions of yourself exploring different paths at the same time. If any of them reach an accept state, the whole input is accepted. Now here's something fascinating. DFAs and NFAs are different in structure, but they recognize the exact same class of languages, the regular languages. A regular language is any language that can be described by a finite automaton. That includes simple patterns like strings that start with A, strings with an even number of zeros, strings that contain cat anywhere. If you can write a regular expression for it, those familiar patterns we use in search boxes and code, you can build a finite automaton to recognize it. Let's say we want to match all strings of digits that contain exactly 3 digits. A regular expression might be 0, 9, 3. A finite automaton could be built with 4 states: start, after 1 digit, after 2, and after 3. After 3, any further digits lead to a rejecting state. That's a finite automaton working behind the scenes of what feels like a simple pattern match. Regular expressions, in fact, are just a different way of writing regular languages, and finite automata are the machines that recognize them. This connection between theory and practical tools is one reason why automata theory remains relevant. It underpins tools we use every day. Now, finite automata also have limitations. They can't count very well. For example, a finite automaton can't recognize strings with an equal number of A's and B's, like ab or ababab. That's because it can't remember how many A's it has seen to match them with B's. There's no stack, no memory beyond its current state. This limitation becomes the boundary between regular languages and non-regular ones. Once you need memory, like balancing parentheses or matching nested structures, you move beyond the power of finite automata into the territory of more powerful machines like pushdown automata. But for many tasks, pattern recognition, input validation, simple tokenization, finite automata are both efficient and sufficient. Let's think about how this applies to real-world computing. When you enter a password that has to meet a pattern, say 8 characters with at least one number, a finite automaton is effectively used to validate that structure. When you search text with wildcards or specific patterns, you're using regular expressions, and under the hood, they're often converted to automata for fast matching. In the early stages of compiling code, a program called a lexer breaks up your source code into tokens, numbers, keywords, symbols, using finite automata to recognize these patterns efficiently. Even in network security, firewalls can use pattern matching automata to scan for suspicious payloads in data packets. So while finite automata are simple, they are also powerful and everywhere. To wrap up, think of finite automata as humble machines. They don't remember much, they don't make decisions with deep logic, but they are fast, predictable, and surprisingly versatile. They form the mathematical backbone of how we understand patterns, and they sit at the very foundation of the theory of computation. From this simplicity, the entire landscape of computational logic begins to unfold. But sometimes patterns aren't flat. They're layered, nested, like code blocks inside code blocks, or parentheses within parentheses. And to recognize those structures, we need something more powerful than a machine that just tracks where it is. We need a machine that can remember dot. That's where pushdown automata come in. You can think of them as finite automata with one upgrade: a stack. Just like a stack of books or plates, you can only add or remove from the top. Last in, first out. This stack gives the machine a limited memory. As it reads a string, it can push symbols onto the stack and later pop them off. That simple act of remembering just one thing at a time, the top of the stack, unlocks a whole new level of capability. Take the example of checking whether parentheses in a sentence are balanced. Every time the machine sees an opening parenthesis, it pushes a marker onto the stack. When it sees a closing one, it pops a marker off. If the stack ends up empty and the input has been fully read, the string is accepted. That means the parentheses are correctly matched. This kind of pattern, one that requires memory and nesting, is beyond what finite automata can handle. But pushdown automata manage it easily. The languages they recognize are called context-free languages. And to describe these languages, we use context-free grammars, a formal set of rules that explain how valid strings can be built. These grammars work like building instructions. You start with a basic placeholder, often called a start symbol. and apply rules to expand it step by step, forming larger and more specific pieces. Eventually, you get a complete, well-formed string, made entirely of symbols from the language. For example, one rule might say, a sentence can be a pair of parentheses around another sentence. Another rule might say, two valid sentences can be placed side by side to make a new one. And there's always a rule that says, a sentence can be empty. These kinds of rules can be used over and over to build deeply nested and complex strings, like multiple levels of parentheses or structured programming statements. This process of using rules to generate strings is how parsers work in programming languages. When you write code, a parser checks if your input follows the grammar. If it does, your code is considered valid. If it doesn't, the computer throws a syntax error. Every programming language, whether it's Python, JavaScript, or anything else, has a context-free grammar behind it. The grammar defines what's allowed and what isn't. And here's something elegant. For every context-free grammar, there is a corresponding pushdown automaton. The grammar generates the strings. The automaton recognizes them. Two different tools working with the same idea. Still, pushdown automata have limits. They can handle structures that require one level of memory, like nested expressions or matching brackets. But if the pattern becomes more complex, for example, matching 3 separate types of symbols in equal numbers, one stack just isn't enough. For that, we need more power than a pushdown automaton can provide. But for the vast majority of the structured languages we use in computing, from arithmetic expressions to the logic in a program, context-free grammars are the tool of choice. They give us a precise, formal way to describe syntax, and they help machines understand code the way we do. So, with just one stack and a handful of rules, we move from recognizing flat patterns to understanding structure, hierarchy, and logic. And now that we've explored machines with memory, it's time to ask a bigger question. What does it really mean to compute something? In the next section, we'll meet the model that answers that question. A machine not limited by stacks or states. A machine that can simulate anything we can write down, calculate, or even imagine. That machine is called a Turing machine. If pushdown automata gave us memory, Turing machines give us freedom. So far, we've seen machines that process inputs step by step, with some ability to remember, either through states or a stack. But even the most complex patterns we've looked at have limits. Some problems simply can't be solved by machines like these. That's where the Turing machine enters the picture. It's a theoretical model, not a machine you can buy or build in a factory, but a concept. A simple, powerful idea that captures what it means to compute. Picture an infinitely long strip of tape divided into squares. Each square can hold a symbol, maybe a letter, a number, or just a blank. This tape is the machine's memory. Unlike a stack, the tape isn't limited to the top. You can move left and right, write to it, or read from it, as needed. At the center of it all is a read-write head. It moves along the tape, one square at a time. At each step, the machine checks 2 things. What symbol is under the head? And what state the machine is in. Based on that, it decides 3 things. What symbol to write, which direction to move, left or right, and what state to enter next. That's it, and yet from this simplicity, something profound emerges. A Turing machine can simulate anything, any algorithm, any logic, any process that can be defined by a set of rules. It can add numbers, simulate a computer program, sort data, or even emulate other machines. It can mimic a calculator or act like a language parser, or explore the behavior of natural systems. The tape gives it unlimited memory. The rules give it logic. Together, they define computation. This idea, that the Turing machine captures the full power of algorithmic thinking, is at the heart of the Church-Turing thesis. This thesis, proposed independently by Alan Turing and Alonzo Church in the 1930s, suggests that anything we can compute, anything that can be expressed as a well-defined procedure, can be computed by a Turing machine. It doesn't matter how complex the program is or what language it's written in. If it can be done at all, it can be done by a Turing machine. That's a bold claim, and it's never been disproven. In fact, it's one of the most accepted ideas in all of computer science. Turing machines don't just describe what computers can do, they also define what they can't. Because for all their power, even Turing machines have boundaries. There are problems they can't solve, not because of speed or memory, but because the problem itself is unsolvable. The most famous of these is the halting problem. We'll talk more about that later. But for now, let's reflect on what the Turing machine represents. It is not the fastest, it is not the most efficient, but it is the most complete. Any programming language you know, Python, C++, JavaScript, is just a more human-friendly version of a Turing machine. Every app on your phone, every website you visit, every game you play, all of them are ultimately executed by machines that follow the same logical structure. Modern computers have fancy interfaces and hardware acceleration, but deep down, they follow the same rules Turing described nearly a century ago. Why does this matter? Because understanding the Turing machine helps us understand limits. We now have a universal model for what can be computed, and by extension, what cannot. We can stop asking, how do I solve this, and start asking, is this even solvable? That shift is one of the most powerful moments in the theory of computation. It turns computer science from a set of tools into a way of reasoning, a framework for what's possible in a digital world. And so, as the Turing machine hums along its endless tape, we're reminded that computation is not just about machines doing work. It's about understanding the boundaries of knowledge, logic, and decision-making. And sometimes those boundaries are final. In the next section, we'll step into that frontier, where not all questions have answers, where not all programs finish, and where no matter how powerful the machine, some problems remain forever unsolved. Let's explore decidability and undecidability. If a machine can compute anything we can describe, then a natural next question is, what kinds of questions can a machine answer at all? This brings us to the idea of decidability. A problem is called decidable if there exists a step-by-step method, an algorithm, that will always give you a clear answer, yes or no. No matter what input you give it, the process always finishes and tells you whether the answer is true or false. Think of it like this. If you ask a question and there's a guaranteed way to find the answer using a machine, no guessing, no ambiguity, the problem is decidable. Here are a few simple examples. Let's say you want to know whether a number is even. That's decidable. You divide the number by 2 and check the remainder. The answer is always clear, yes or no. Or suppose you're given a word and a regular expression. and you want to know if the word matches the pattern. That's also decidable. Finite automata, like we discussed earlier, can check that with a guaranteed result. These kinds of problems, checking patterns, performing arithmetic, comparing strings, all fall within the realm of decidable problems. There's a clear method, and it always finishes. But not all problems are like that. Some problems lie beyond the reach of decision. These are the undecidable problems. In these cases, there's no general method that always gives you an answer. You might try, you might guess, you might even get the right answer sometimes, but you can never build a machine or write a program that works for every possible case. One of the most famous examples comes from mathematics. Imagine you're given a statement in arithmetic, like a complicated equation involving multiple variables. You ask, is this equation true for all values of the variables? This is a version of a problem called Hilbert's 10th problem, and it turns out it's undecidable. No algorithm exists that can always give you a yes or no answer for every possible equation of that kind. Now let's bring it closer to computing. Suppose you write a program and you want to know, will this program ever stop running? That's a hard question, and it turns out in the general case it's undecidable. You might be able to figure it out for small programs, or for programs you wrote yourself and understand completely. But no program can exist that correctly decides this for all possible programs. We'll explore this idea in more detail in the next section. It's called the halting problem. But the key point here is this: some questions simply have no algorithmic solution. And that realization is one of the most profound in all of computer science. It tells us that limits are real, not because of hardware, not because of time or memory, but because the universe of logic itself contains problems that are forever unresolvable by any machine. Now you might wonder, if undecidable problems exist, how do we recognize them? That's where theoretical tools come in, like reductions. A reduction is a way of showing that one problem is at least as hard as another. If you can take a known undecidable problem and transform it into a new problem, and solving the new one would also solve the old one, then the new problem must be undecidable too. This is a common technique in theoretical computer science. We prove a problem is undecidable not by solving it, but by relating it to another problem we already know is unsolvable. It's a little like a logic puzzle. You can't open the locked door, but if you show that opening this new door also opens the first one, and you know the first one is locked forever, then the new door must be locked too. This helps us map the boundaries of what machines can do. Inside the boundary are the problems we can solve, the decidable ones. Outside lie the undecidable problems, forever unreachable by algorithm alone. This doesn't mean all hope is lost. In many cases, we can still work with approximations, heuristics, or domain-specific rules. Just because a problem is undecidable in general doesn't mean it's impossible in practice. It just means we need to know where the edge is, so we don't fall off it. In the end, decidability is about understanding the shape of computation. It's about knowing which questions can be answered and which ones must remain open. And with that in mind, we now turn to the most iconic, undecidable problem of them all. A problem that looks simple, that starts with a perfectly ordinary question, but leads to one of the deepest results in logic and computer science. Let's talk about the halting problem. Here's a question that seems simple on the surface. Given a program and some input, will the program eventually stop, or will it run forever? This is the essence of the halting problem. It's a natural question. If you're writing code, you often want to be sure it won't get stuck in an infinite loop. You might wonder, can we write a program that looks at other programs and tells us whether they'll halt or not? It turns out we can't. This question, whether a program halts on a given input, is one of the most famous examples of an undecidable problem, and the proof, offered by Alan Turing in 1936, is both simple and brilliant. Let's walk through the idea. Imagine you could build a program, let's call it the halting checker. This program takes as input another program and some data. It looks at them, analyzes the logic, and tells you, yes, this program halts, or no, this one runs forever. That's the dream, a universal bug checker, a way to guarantee that your code won't hang. But here's where things get strange. Turing imagined, what if we feed this halting checker a very special kind of input, something a little paradoxical? Suppose you write a program that does the following. It takes in a description of another program and uses the halting checker to see if that program halts when run with its own code as input. If the program does halt, this new one goes into an infinite loop. If the original doesn't halt, this new one stops immediately. So it does the opposite of whatever the original would do, but using the halting checker to decide. Now here comes the twist. What happens when you feed this new program itself as input? Think about it. If it halts, that means, according to its own rules, it should loop forever. But if it loops forever, then it should have halted. It contradicts itself, a paradox, and this contradiction tells us something deep. No such halting checker can exist, not because we wrote it badly, not because the computer is slow, but because the very idea leads to a logical contradiction. This is Turing's proof. He showed that there's no general method, no program, no algorithm that can look at all other programs and always correctly decide whether they'll halt. And that result changed everything. It told us for the first time that there are limits to what we can know about programs. Not because we're not smart enough, not because we don't have the right tools, but because some questions simply have no answer within the system. And this isn't just an edge case. The halting problem is connected to many other undecidable problems. It forms the foundation for understanding why certain bugs are uncatchable, why some analyses can't be automated, and why no compiler or language can protect you from all infinite loops. It also inspired future discoveries in logic, in mathematics, in artificial intelligence. In many ways, the halting problem is a doorway. It opens onto a deeper truth that even in the precise world of machines and logic, some things remain unpredictable. Some outcomes can't be known in advance, and some systems, no matter how carefully built, will always contain a hint of mystery. And maybe that's a fitting place to end this journey. From the simplest machines that recognize patterns, to grammars that define language, to theoretical devices that simulate all computation. We arrive at a boundary, a line that marks what can be computed, and what lies forever beyond. And now, as the tape unwinds and the machine slows to silence, you can rest, knowing that even the sharpest logic contains its own quiet unknown.